Hey there, let me show how to view members of a class in an optimized release mode application. So, in my previous video, I showed how to view local variables in an optimized release mode application when the symbols are stripped. In that video, I showed a little bit on how to use assembler listings to find the location in which a variable can be viewed. The same technique can be used to view classes as well. Let me switch over to my sample application. This application is written specifically to illustrate the concept, so there's nothing special about this application. Let me show this class, which is my test object. This class has three variables which we are going to find within WinDebug. For simplicity, the variables are initialized to these values so that it will be easy to find these values within WinDebug. This class is instantiated within onInit dialog. That's just one method call over here. We will use this as the location to inspect the object. Before we begin, there are two settings we need to enable. The first is that we need to configure assembler listings. So we go to C++, we go to output files, and we set the assembler output to be everything. We want to use assembler listings to find the location within the executable that we can put our breakpoint. The second option is to set that the symbols are stripped. The reason we set that the symbols are stripped is because this is representative of most release mode applications in which all the Windows APIs are stripped. So we're gonna do this demonstration with stripped symbols. Finally, I'm using a 32-bit application because it kinda looks neater in WinDebug. Now let me switch over to WinDebug. WinDebug is waiting at a breakpoint for onInit dialog. Let me drag in the source code file. There we are. Let's make the screen a bit neater. Let me just move this window up here and reposition it slightly, like that. We can see in the source code that there is no syntax highlight for onInit dialog, even though the breakpoint has already reached onInit dialog. This is correct because when the symbols are stripped, WinDebug does not know where in the source code the breakpoint has hit. Let's run the program until test object print value. The quickest way to find this location is to just view the assembler listings. So I've opened the assembler listings which I got from the hard disk. In my previous video, I showed how to get to the assembler listings, but all you need to do is configure in Visual Studio that you want assembler listings. And then when you compile the program, the assembler listings is in the COD file in the same directory as the executable. Once we have the correct file open, just search for the line that we want to go to. So I want to go to this line, test object print value, and the assembler for this line is basically just dereferencing the variable test object which is on the stack and calling the function print value, which is just compiled using this symbol over here. This is just the name mangling of C++. This part over here explains what it is in English. So what we need from here is just this memory address. Now we go back to WinDebug and we use that address. So we add the breakpoint like this. So that address is an offset. So we take the start of onInit dialog and we just add it with that offset. And that will add a breakpoint further in the function exactly at the point of calling print value. So let's run the debugger all the way to that position. So if I press go one time, two times, I will hit exactly on print value. Now, if we try to view the local variables like this, we are gonna get that there are no symbols. This is what happens when the symbols are stripped. Now, we can see in the assembler that the stack location 20 is being used to store the object. The pointer to the object is then put into ECX and a call is made. But if we try to view ECX, we are gonna get that there is no symbol at that location. This is also correct because when the symbols are stripped, there really is no symbols for types. What we can do is that we can query the ECX register to find the member variables. How this works is that in C++, the this pointer or the object pointer is actually a parameter of the function. This means the memory address of this pointer is now located within the ECX register. So let's do that from here. If we run DT, it won't work. If we try to force DT by putting the type, it also won't work because the type really cannot be found. What we need to do is actually query each member by knowing its memory offset. Let me drag in the source code to take a look. So if we look at the source code, there are 3 member variables. And so the way that the ECX pointer will be arranged is that this will be the first member variable, this will be the second member variable, and this will be the third member variable. We can actually deduce this by also looking at the assembler listings. Let me switch over to the assembler listings. If I go to the assembler listings for mytestobject.cod and I search for the constructor, I can find that, let me just search again, I can find some assembler for the variables being initialized. The first variable, local number, is being initialized to the value 12. The next variable, precision number, is being initialized to the floating point equivalent of 10.5. This is just the floating point encoding because floating point numbers are encoded different. This is an IEEE format. I won't cover this format in this video, you can Google for it, but this is exactly correct to the number 10.5 float. And the string is being initialized as this segment, which is located up here. The way the segments work is that the string is constant, so it's actually written as a segment, and the segment is taken from there and just inserted into ECX plus 8. I can see that the value of ECX is the first variable, ECX plus 4 bytes later is the second variable, and after another 4 bytes is the third variable. Let's switch back to WinDebug. Let me drag in the constructor source code. There we are. So we can see from here we have a local number 12, a precision number is 10.5, and the string value over here is just the word sample string. So because we know the offsets, we can just inspect ECX. So if I run dd ECX, what I get is, I get that the first value over here, C, this is the number 12. There we are, the number 12. So we know that the first 4 bytes is the first variable. We also know that the second variable is 4 bytes after the first. So if we run df ECX plus 4, what we will get is, we'll get the value 10.5, which is exactly correct for the second value. Now the third value is a string pointer. So to view that, we do du, which is Unicode, POI ECX plus 8, because we know it is 8 bytes later, and we get the value sample string, which is exactly correct. The reason we use POI is because this memory address over here is not actually the string, it is a pointer to the string. So POI dereferences that memory location and then it gets to the string. And that, in a nutshell, is how you view objects when there is no symbols. This demonstration looks complicated, but if you try it a few times, it becomes second nature to try to deduce what member variables are located within objects and structures. I use this technique a lot because the Win32 API is always stripped symbols. So there is no choice because you can't use DT to view structures. Instead, I just view the individual members by viewing the memory directly. Let me know in the comments below if you have used this technique before. And a gentle reminder to subscribe, hit that bell icon and give a like if you like the content. As always, it's been a pleasure bringing you this information. I am High Voice, signing out.